Example 8.2. A slit 5 microns wide is illuminated by 540 nanometer light. The diffraction pattern is observed on a screen that is 2 meters from the slit. The intensity at the center of the central maxima is 6 times 10 to the minus 6 watts per meter squared. In other words, 6 microwatts per meter squared. A, what is the screen locations and the relative intensities of the first 4 maximas? How do they compare to the actual values? B, what is the intensity at a point on the screen midway between the center of the central max and the first minima? Before we answer these questions, let's get the details of the diffraction pattern. So as usual, we start with the diffraction parameter. And we see here is that then n max is then going to be a over lambda. So if I start to put my values in, this is going to be 5 microns divided, and remember, I'm converting the wavelength of light into microns. This is 0.54 microns. So that should be roughly around 10. So this should be 9.26. And this is N max. So then what I'm going to do here is I'm going to try to fit everything onto one line right here. So let's see if I can do that. So what this tells me then is that if I look at my minimas, I'm now looking at the integer value. So the nearest integer to 9.26, we have ND equal to 9. And that tells me then that the total number of minimas is going to be 2 times 9, which will then be 18 minimas. And of course, this is on both sides. And then I have my maximas. So when I look at my maximas, I look at my value that's closest to a value of 0.5. And you could see here that the closest to this thing has to be 8.5, because if I go to 9.5, I now exceed N max. So therefore, NC has to be 8, because it's 8.5. And then the total number of these guys is then going to be 1 plus 2 times 8, which will give me 17 maximas. And I should be careful when I say this, because what this really tells me is that this is the full number of maximas, the full brightness of the maximas, or secondaries at least. And then what we're seeing here is that what I have here is that I have partial maximas, and so when I look at the partials, we see that this is 9 plus 0.26. So what this is telling me right here is that this right here is a partial. It's just slightly closer to the maxima than the minima, but that's where I'm getting my partials from. So what this tells me then, that I now have two partial maximas. So now, if I look at everything and I put everything together, I really have 18 minimas, and I should be able to see 9 maxima somewhat. Of course, the two partials are dim. So when I look at the diffraction profile, if I draw this out, then I'm going to be looking at something like this. So what I expect to have here is that since I have 9 minimas, I have to go out at least to n equals 9. So then I'm going to go 1, 2, 3, and then I'll put my dots here. And then what you're going to see here is that I'm going to come up here and I'm going to go here, and then it's going to go up and it stops right there. So I know that right here, this is 90 degrees. So that's the little partial that's around halfway up here. So now if I start labeling my n values, this will be 1, 2, 3, and then this has to be 8, and this has to be 9. If I look at my maximas, then this guy here has to be 1.5. Remember, that's approximate. This is 2.5. And then right here, this is 8.5. And then the peak here will be 9.5. Those are my values of n. So if I look at my alpha values, remember, alpha is where sine of alpha goes to 0. So then alpha is then going to be pi, 2 pi, 3 pi, 8 pi, 9 pi. And by the way, this should be that 10th minima right there. So when I look at this spot, what I'm seeing here is this little spot right there. This is what gives me 9.26. So here's my intensity profile. So now what I want to do here is that I want to calculate the angular and screen locations for the first 4 maximas. Now that's a lot of maximas, but there's a reason to this madness, because we really want to compare the approximated values to the actual values. So here we go. So the angular and screen locations for the first 4 maximas are going to go like this here. So I'm going to start off with the angular locations. And what do we know here? Well, I know I got to use the path difference equation. So the angular locations really tell me that I have to solve a sine of theta, and this is approximately equal to NC plus 0.5 times alpha. That's our equation. So if I take the sine inverse of this thing, I'm going to get, let me kind of guess where I'm going to draw this here. Let's say, let's start here. So this is going to be equal to sine inverse of NC plus 0.5 divided by the diffraction parameter. And so if I put in my values, then this is really just sine inverse of NC plus 0.5 divided by 9.26. Now remember, what I should be saying, I'm going to drop this down a little bit more. Where NC is then going to be 1, 2, 3. Now note it's plus or minus, but I'll add the plus or minus at the end. So here we go. So if I look at the first one, this is going to be sine inverse of 1.5, 9.6. And when I look at this, oops, I did not draw this well. So let me try this again. So this is going to be 9.26 of 1.5. And then I'm going to get plus or minus. And if I calculate this number, I'm going to get 9.32 degrees. And this will be the approximate value of theta 1. Now, since I'm going to repeat this calculation again and again, I'm going to copy this, and then I'm just going to put in the values. I'm going to modify each of these because this is a lot of points. So now I'm going to come back with my eraser, and I'll make the adjustments for the values of n. So here we go. So now I'm going to come in, and this is not 1, it's 2, that's 3, that's 4. So then I'm going to come in and I'm going to put that this is 2, 3, 4. So now I got to come in and change these angles because they're not going to be the same. So when I calculate these angles, this will be 15.7. This will be 22.2. And this will be 29.1. Where this is now going to be 2, 3, 4. So when I look at these are my angular locations. And we're going to need these for the screen locations of the maximas. So now let's repeat the same process for the screen locations. So now if I look at the screen locations, we're going to use the relationship y of n of d10 of theta of n, but in this case, the screen is 2.0 meters times the 10 of theta like that. So I'm going to repeat the same calculation again. So you could imagine what I'm going to do here is that now I've just got to put these angles into this relationship. So this is going to be 2.0 meters. And then this will be the 10 of the angle that we calculated above, which will be this guy right here. And in this case, I'm going to get plus or minus. Putting this into centimeters, I'm going to get 32.8 centimeters. And that's going to be the approximate location of y1. Now, because this is a repeat, I'm just going to paste and slightly modify this so that we can move quicker. So now all I have to do is that I have to go back and I have to change these angles right here. And I'm going to have different values for my locations here. So here we go. I'm going to put in the angle of 15.7. When I do, I get a value that reads 56.2 centimeters. Then I'm going to put in 22.2, and this is going to give me 81.6 centimeters. Then I'm going to put in an angle of 29.1, and that's going to give me 111 centimeters. And this will be for 2, 3, and 4. So these are the approximate locations of the screen locations of the maximas. And again, this is all about y of n equal to d tan theta of n. Now, we've used the Phys applet numerous times in lecture, so let's go look at that. So I'm not going to go into the applet. I'm just going to, I took a screenshot of it. So using the Phys single slit diffraction applet, let's get the exact values of the angular locations of the maximas. So I did this for the first 4, so that's what we're going to compare. So when I paste this in, here's what the applet is looking at, and you can see right here is that these guys are the applet values. And this one uses the actual value that you calculate using the very complicated integrals. These values that we have right here, these are the approximated values. Okay, so these guys right here, these are the approximated values. So what we want to do is that one way to compare them is to take a percent difference. So what we're going to do here is to compare the exact versus approximate I will compute the percent difference. The actual values are the ones in the applet. So let's go do this. So if you look at, I think that's a little bit too high. So look at K1 is the same as N1. So you could see here, so if I look at the percent difference of theta 1, this is going to be, so look at the approximate value is 9.3. So it's going to be 9.32 minus 8.90, but the actual value is actually 8.90. And then I'm going to multiply this by 100%. And what you're going to get here is that this is a 4.72% uncertainty. So then I'm just going to repeat the process. So if I repeat this process, to speed things up, I'm just going to take these values and I'm going to keep just like I did before. I'm going to paste it and then slightly modify it so that we spend very little time in this redundancy. But it's important that you actually see them. So what you're going to do here is that I'm not going to show you these values. So you could see that this is 15.4. This is 22.0, this is 28.9, and then we have these values right here. So I'm going to move fairly quickly to just put these guys in here. And of course, these are going to be, and what I really want to show you is the trend of what we're actually seeing. So here we go. So K2 versus, or N2 for both of them, the approximate here is a little bit higher, so I'll put that one first. And then this is going to be 15.4, and this is going to be divided by 15.4. So if you compute that value, this is 1.95%. You could see that the percent has decreased. Now, if I put in 3, you could see here that I get 22.2, and then 3 here is 22.0, but 22.0 is the actual value. And the next thing that you see here is that this is 0.9 1%. And then if I go to 4, we see that our values here are going to be 29.1, whereas 4 here is 28.9, but 28.9 is the real value, and you get now a value of 0.69. So what you're seeing here is that as we get more terms, right, you're seeing a trend that as we get further from the central max, that there's a decrease between the exact versus the approximate value. So the further I get away from the central maximum, the better the values get. So at some point, we got to ask, what's the sig figs here? So here you can look at theta 4 to 3 sig figs. This is 0.7%. That's pretty good approximation. If I was to go higher, they get better and better and better. That's why the approximate is really good as we get further and further. So now, because of this, we can then say that it's not I agree that if you look at the first angular location, it's off by 5%, 2 is 2%, and then at 3 and 4, we're under 1%. But if you're willing to live with that, then the mathematics is a lot easier. So now what we want to do here is that we want to calculate the intensities. So to calculate the intensities, we need the phase factor. So now that we have the approximate locations of these secondaries, we need to calculate the phase factor alpha. So we know that alpha must be pi a lambda sine of theta. But if we use the path difference equation, we know that this guy is going to be NC plus 0.5. And we know that that's a good approximation, except for, the first two, we were off by 5 to 2%. And we know that this value here, these are odd half integers. If these are odd half integers, that's when sine of theta is always 1. So now if I plug these in, now remember this is approximate, this is going to be NC plus 0.5 pi, because remember I got AC, A sine theta is now, NC plus 0.5 times lambda. The lambdas cancel out, so I get these odd half multiples, and we could then say that this becomes plus or minus 1.5 pi, plus or minus 2.5 pi. And you can see how this continues to move here, the pattern. So this guy is, of course, the first secondary, the second secondary, and then etc. So now the relative or the approximate relative intensities for these secondaries then goes by this relationship. So it's going to be I relative, and this is going to be IN over I initial, and this will then be sine of alpha over alpha squared. But remember, alpha is these odd half multiples here. So then what you're going to see here is that then this, I can then approximate this as sine of NC plus 0.5 pi divided by NC 0.5 pi, and then this whole thing is squared. But the issue here is that this is 1. This guy right here is always going to be plus or minus 1. So then I can simplify this relationship to read NC plus 0.5 squared pi squared divided by into 1, and that's going to be my relative intensity here. So this is how I'm going to calculate my intensities. So I'm going to apply this to the first 4 maximas. So let me move my screen up. And so here, so now let's calculate the first 4 maximas. So I'm going to move down here. So I'm going to say that the relative intensity, which we already know is going to be proportional to NC, it's going to be equal to . 1 like this, and remember, NC is going to be 1, 2, 3, 4 for our situation. So then here I go. I'm going to say that our first relative one, for n equals to 1, this should be 1 plus 0.5 squared pi squared into 1, right? And we know that's approximate. And when you calculate this thing, you know, I'm going to not put this in here. I'm just going to save space here, I'm going to look at this guy right here. That's for n equal to 1. And when I calculate this, this is 0.0451. Or I can write this as 4.51%, which is approximately equal to the relative intensity of 1. Now, because I'm going to repeat this, I'm going to try to move quickly through this. So to not be super redundant, again, there's a reason why I'm doing this. So now what I'm going to do here is that then I am going to calculate all of these for the first 4 values. Uh-oh. I don't know what I just did. Oh no. I must have deleted this thing. So I'll have to come back and rewrite it here. But now let's go modify this. This is 2. So we know that this guy is 2, 3, 4. We know that these values are going to change. Okay, we know that they have to change. And then these are going to change, of course. So now here I go. So if I calculate this, this is 0.01162. This is 0.831. This is 0.500. So if I now look at the percents here, this is 1.62, 0.831, and then this is 0.500. And these are my relative intensities. So I better come back here, and this is I relative, which is then going to be a function of alpha. And these are the values. Now, the first thing that we should do here is that we should add these percent differences. Not percent differences, but these percentage values. So now what I'm going to do here is that I'm going to add all of the percent intensities for one side of the diffraction parameter or the diffraction pattern. Now, the reason why we want to do this is because we've claimed that the central max has 85% of the intensity, while all of the remaining secondaries have approximately 15%. So let's see if this is really the case here. So the first thing that we want to do here is that I'm going to add all of these percentage points. And so what you're going to see here is that the first value that we get here is if I add these all add up to 7.46% for one side. So now here's the thing that I find really interesting. For both sides, we need to multiply this by 2. And if you do that, this is going to be 2 times 7.46%, which tells you that this is 14.92%, which is the intensities. You know what? I think I'm going to move this because I'm running out of space. So I'm going to move it right here. So then if you look at this, we now have this value, and this is the intensity of the first 4 secondaries. So as we go to NC equal to 5, 6, 7, they get way dimmer. So from this, we see that the remaining secondaries beyond NC equal to 4 are extremely dim. All of them, all the way up to n equals to infinity, I guess, or to the end of the diffraction pattern, will then get 0.08%. Now, let's do the last part of this question, and we're now at C. And what we want to do here is that what is the intensity midway between the central max and the first minima. We know its location, right? We know this location approximately. Well, if it's exactly in the midway, we know its location. So its location then has to be here. So if I now look at my pattern, we know that this guy is going to look something like this. And we know here so if I look at this, we know here that this is going to be n equal. So if I look at alpha, we know that this guy has to be 0. This is going to be pi. This is going to be 2 pi. So if I look at exactly the middle between these two has to be pi over 2. Now, what happens here is that now that I have that, I know the location of alpha, so I can do this here. So the location of this point is alpha, which is then going to be pi over 2. Now you gotta be careful here because pi over 2 means that it's in rads. But I know that this has to be sine of theta divided by lambda. So right away, I know that the angular location is then going to be given by this relationship. So right away, if I solve is given by sine of theta. So if I look at this, we see that we have sine of theta. You could see that the pi's cancel out. And so then I'm going to be left with lambda over 2a. Now I'm going to get what that angular location is. And then I'm going to get the sine inverse of 2 times, what was my value here again? My value, that seems like an infinite amount of time ago, is 9.26. So I got to come back here, and this is going to be 9.26. And I have to get this angle right here. So this numerical value ends up being 3.10 degrees. So the screen location is y of alpha equal to pi over 2. And this is going to be d, which is 2.0 meters, times the tangent of 3.10 degrees. And I get a value of 0.108 meters, or 10.8 centimeters for this location, which is alpha equal to pi over 2. So I now know the location of where that is at. So then the relative intensity is I relative, and this is going to be for alpha equal to pi over 2. Now note, sine of pi over 2 is 1. So if I just substitute this, this will be pi over 2 divided by pi over 2. And I square that. And when I calculate this, I get 0.405, or this is 40.5% of the central max. Now, if we wanted the exact intensity, we could then go in and get the value that was given here and the exact intensity that they tell us here. So the actual intensity is then going to be I relative, which is 0.405. This is equal to the intensity at alpha equal to pi over 2 times the maximum intensity, or the initial intensity, which then tells us that now we can then solve for in at pi over 2. So if I do that, this will then be in at alpha equal to pi over 2. The actual intensity given is then going to be 6 microwatts per meter squared. I should write this out. This should be 0.405 times I max, which will then be 0.405 times 6 microwatts per meter squared. So if we calculate that number, we get that this is actually 2.43 microwatts per meter squared, and this is the value of the intensity at alpha equal to I over 2.